So, welcome to a short video on the reactivity of metals and how we use metals, or how we use the reactivity series to predict how to extract metals from their ores. Now, at no stage in the GCSE exam will you be asked to regurgitate the reactivity series, but it is important you know the series and know how to apply the principles of the series. It's also important you know the positions of carbon and hydrogen in the series, and we're going to talk about that now and talk about why that's important. It might be a good idea to have in front of you the periodic table. This is really your memory jog for an exam, and it's important you refer back to that as we're going through. It also helps you balance chemical equations. Now, you should know from your lessons that a more reactive element displaces a less reactive element from a compound. So we can use our reactivity series to predict when reactions occur. So we've got magnesium here. Will magnesium react with hydrochloric acid? Well, we can decide on that using the reactivity series. Magnesium is up here, hydrogen is down here. So as magnesium is more reactive than the hydrogen, the magnesium can come in and kick the hydrogen out of the hydrogen chloride or the hydrochloric acid. And that forms, that new compound is magnesium chloride. The hydrogen has been kicked out, so that leaves us with hydrogen gas. Now, it's not simply good enough to write MgCl plus H. We need to account for our valencies. And if we use the periodic table, we can see that magnesium is in group 2, so has a valency of 2, and chloride is in group 7, so has a valency of 1. And that means we need 2 chlorides for each magnesium. We should also know that hydrogen gas is not just H. It bonds covalently with another hydrogen atom to form a hydrogen molecule, H2. We shouldn't leave an equation like that either. We should balance it. We can see that we've got 2 hydrogens and 2 chlorines on this side, so we need a 2 in front of the HCl. So that brings us on to the second displacement reaction. Will copper displace hydrogen in this reaction? Well, let's find copper on the reactivity series. It's down here. It's actually below hydrogen. So copper cannot displace hydrogen from a compound. So that reaction won't work. Now, in an exam, they might ask you for predicted observations. So obviously, in number 2, nothing is going to change. But in number 1, you're going to see a colourless gas being produced. You will also see the magnesium metal effectively disappearing. It forms magnesium chloride, which is soluble, so the magnesium metal gets smaller. And applying these to a practical situation in the lab is very important. We as chemists can apply the principles of these reactions to using these in industry. Can we use a displacement reaction to obtain a metal from an oxide? Now, this is very important because most metals are found in the ground as oxides or ores. And so we can decide if carbon can be used to extract magnesium out of its ore. And we do this again by looking at your activity series. So let's find carbon, it's up here, and let's find magnesium, it's up here. Now, carbon is less reactive than magnesium, so carbon cannot come in and kick the magnesium out. So we can't use carbon to obtain magnesium metal in industry. It's simply not reactive enough. Could we use carbon to extract the iron? Well, let's find the carbon. The carbon's up here. The iron is down here. So carbon is actually more reactive than iron. So the carbon can come in and kick the iron out, leaving behind iron metal and carbon dioxide. And if we're going to balance that, we should make a good job of it. So let's try, well, we've got 3 oxygens here, 2 over here. So let's try and putting a 3 there to make up to 6 oxygens, which means we need a 2 there. That means we have 4 ions, and the carbons aren't balanced, so we need a 3 there. So we could use carbon to extract iron out of its ore in practice, and we do. Would it work with lead? Well, carbon is more reactive than lead, so carbon can come in and can kick the lead out. We form Pb, and the carbon then goes with the oxygen and we form CO2. Okay, now in order to balance that, just put 2's in there. And so we come to aluminium, a very, very useful metal. Can carbon extract aluminium from its ore? Is carbon reactive enough to do this? I'm afraid the answer is no. The carbon cannot do that. Carbon is lower than aluminium, so the reaction doesn't work. We put a cross through it. So that is why we choose certain methods to form certain metals. Now, if we just scroll forward, just a slight technical hitch on the computer, my Bob, to looking at displacement reactions and how these reactions work if we were doing these with solutions. Now, let's have a look at zinc and copper sulfate solution. Zinc, a grey, shiny metal, and copper sulfate, a blue solution. Would we expect that reaction to go? Well, look back at your reactivity series. Is zinc above copper in the reactivity series? And the answer is yes. So zinc comes in, kicks the copper out. So shouldn't say zinc there, we should say copper, and therefore leaving behind zinc sulfate. Now, what would we see when we do that reaction? Well, zinc is a grey, silvery metal. What does copper look like? Okay, copper looks very different. Copper's an orangey metal. So the solid turns from grey and silvery to orange. Probably also a little bit shiny if it's good quality copper. Copper sulfate solution. Well, you should know copper sulfate solution is quite a frequently used one in the laboratory. It's a blue solution. Zinc sulfate, it's not blue, it's actually colourless. So the blue solution gets paler and paler and paler until it becomes colourless. We don't see any gas being evolved, we don't see any bubbling, and the reason for that is because you're not producing any gas. Copper is a solid, zinc sulfate is a solution. The ionic equation for this, well, that's a little bit more difficult, but if we look at the sulfate in here, the sulfate doesn't really do anything. Okay, differently on the left as on the right. It's still floating around in aqueous solution. However, our zinc changes. Our zinc goes from zinc metal to zinc in solution, and as it's bonded to a sulfate, we know now that zinc has got a charge. We can see that from here. Sulfate, we should know the charge is 2 minus, and zinc is 2 plus. So we actually go from zinc solid to zinc aqueous, which has a 2 plus charge. What about the copper? Well, the copper actually does the reverse, does the opposite. The copper over here is 2 plus. We can see that because it's bonded 1-to-1 to a sulfate, and we know that sulfate is 2 minus. If you're unsure of that, look at your valency sheet. And the copper goes from 2 plus to being copper without a charge. And if we're writing an ionic equation, we have to check the charges on the left and on the right. 2 plus in total on the left, 2 plus in total on the right. So the charges are balanced. And then I've written here, as a reminder to myself really, is it a redox reaction? Well, let's have a look. The zinc goes from being neutral to being 2 plus. How does it go from being neutral to being 2 plus? Well, if it becomes positive, it's lost negative particles. Okay? It's lost electrons. So the zinc loses electrons. What happens here? Well, the copper goes from being positive to being neutral. In order to go from being positive to being less positive, it must be gaining negative particles. So the copper 2+ actually gains electrons. And if we think back to our definitions of oxidation and reduction, we should know oil rig, oxidation is loss. So the zinc has been oxidized, and the gain, reduction is gain, and the copper is reduced. So we can see that this is actually a redox reaction. We've got reduction and oxidation occurring both at the same time. And the next video we will look at applying our displacement reactions to extracting metals in industry, and that's a very popular exam question.